Welcome, everyone. And today's lecture, we're going to cover a special type of integer programming problem called self-covering problem. It's a very famous problem, standard problem in facility location. Give you a very easy application to begin with. We'll learn how to locate as few fire stations as possible, but provide sufficient coverage for the possible emergency response within 15 minutes of a 6-neighborhood city. In this example, you will learn how to solve the set covering problem. We show you how to construct an integer programming problem model, implement the model in Gurobi-Python API, and find the optimal solution using Gurobi optimizer. This model example we're going to show you right here, problem station. There are 6 cities in Gurobi County. The county must determine where to build the fire station. The county must want to build as less number of fire stations as possible, but provide sufficient coverage within 15 minutes of driving time for each city. So this data is going to give in below in a second. And solution approach, we're going to set T equals to the set of a potential city to build a fire station. R is the index of a set of cities. They are basically the same, but using a little bit different later on. And the graph R and E, R represents a set of city, and E represents the set of arc, which is a possible arc from city I to city J. So, okay. And parameters, and we have a few parameters. And first is the cost to build a fire station at city I, and different city may have a different cost. PJ is the population of city J, for example. The coverage IJ represents the possible coverage within 15 minutes distance. Okay, I got 2 separate decision variable. One we could have covered, okay, and equals to z 0 and 1, and the variable equals to 1 if the j is covered and otherwise 0. And the second decision variable called built sub I is also a binary variable. The variables is equal to 1 is the fire station is installed in the city I, and otherwise build I equal to 0. Okay. Objective function is minimize the number of fire stations need to build, and this is the equation. The minimize the z equals to the summation of the build sub I. So we want that as less number as possible. And for this example, we only have one constraint called coverage. And for each region, which each city belongs to R, ensure that at least one fire station with a 15 minutes range that covers the region must be selected. So therefore, total number of for each one of a coverage, each cities of coverage, total number of summation of BOI is greater than or equal to 1. And that means the city can be covered by multiple fire stations, but each fire station has to cover a certain part of the city, and each city has to be covered at least by one fire station. So these are the theoretical models, and then we jump into the Python implementation. The example, we have a 6 city, and these are the driving distance in terms of minutes, travel time, in terms of city I to city J. For example, city 1, and these are the driving time. If I have a 15 minutes limit, actually, if I build a fire station in city 0, and that means this fire station can only cover city 0 and city 1. City 2, 3, 4, and 5 are out of 15 minutes range. Okay. If I build a city in city 1, then I can cover city 0, city 1, and city 5. But city 2, 3, 4, I cannot cover in that case. So we can, based on this travel time from to this distance, and you probably notice that they are symmetric, and that's what I'm saying. To and froms are exactly the same distance. Defining the decision variable, we have xi, which is the build sub I, equals to 1 if the fire station is built in the city I, 0 otherwise. My objective function is trying to minimize the z equals to x1 plus x2, x3 plus x4 plus x5 and plus x6. So 6 city total, if how many fire station I need to build, and we want to minimize that. I can convert this table right here and into a so-called accessible or coverage table. So for example, CT0, I can cover CT0 and 1. CT1, I can cover CT0, 1, and 5. CT2, I can cover CT2 and 3. CT3, I can cover CT2, 3, 4, and so on and so forth. Okay? Because the Python list and array, they all start with 0, so I converted this from 1 to 6 to 0 to 5. Okay, also, if you see that for the first city, okay, which is this guy, so x1 plus x2 has to be greater than 1 in that case. Okay, and that means, and also, okay, we are sure x1 and plus x2 cannot both equal to 0. All right. Also look at the city 2 in the 50-minute range. x1 plus x2 plus x6 is greater than or equal to 0. So one of those has to be equals to 1 in the other case. In that case. Okay, so the overall mathematical formulation is minimize z equals to summation of xi. Okay, and then for each one of the city, they have the so-called coverage constraint. Okay, so pretty much we have situation right here. Now is the Python Gurobi API implementation. And first, we're going to import the Gurobi-Python library as a GP. And the GRB is actually the data structure and the parameter input. So I defined two so-called Gurobi-Python multi-dimension dictionary. And first is the city against population. 0, and we had 590 people. City 1 have 690 people, and so on and so forth. The other one is the city coverage and cost dictionary. City 0 can cover 0 and 1, city 1, and the cost will be 4.2. Okay, and the overall budget is 20. Okay, probably 200,000 or $2 million. But these are the corresponding costs. See how much we have to maintain is less than this budget. Okay, could be. And city 1 covers 0, 1, and 5. City 2 covered 2 and 3. City 3 covered 2, 3, 4. Actually, this is a table I'm based on. Okay. So that's pretty easy in a sense. So, and the model, based on this two dictionary, I can build my model. Okay, and first build a model called set covering 1. I'm using a handler m to represent it. Then I'm adding a variable, whole bunch of variable, total how many variable, the number of cities. So I have a 6 variable. They're all binary variables, and we call them built. Okay, so X variable is called build. Okay, and then the next, I'm defining the constraint after defining the variable. I'm defining the constraint. I'm still using m.add constraints. So this is a plural right here. So I'm going to say the sum of the bill over R, which is summation of X, for R is in the city and R is in the coverage. So R is in this coverage. Added them together is greater than equals to 1. Basically follow this, each one of these equation. So if it's in the covers, those two summing up is greater than equal to 1. From this, we can probably tell actually we don't have to worry about it. So if I look at this, it's probably one of x1 or x2, probably x2, and then x3, 4 probably also needs to be select, because 1 and 2 can cover first two city, and 3 and 4 actually can cover. Okay. 1 and 2 can cover first city, second city, and number 6. Okay, and number 3 they can only cover 2. So number 4 can cover the other. So we can, by visualize it, we can see that x2 equals to 1, x4 equals to 1 eventually, and that's our solution. But here I'm just demonstrate you can easily tell this which one is the optimal solution. Will be x2 equals to 1, x4 equals to 1 as well, but we show you how to using a Gurobi library to solve it. So let's run this. And summation of the bill for the R's in the city as an index, and R's are also in the coverage of. And for the T is each one of the city is greater than equal to 1. We'll call the builder to cover. Okay, build to cover is our constraint name. And finally, we set the objective function equals to the sum of all the bill T, and when T is in all the city. And my objective is trying to minimize the objective function. After I define the objective function, constraint, and variable, now I should run a quick update. So save all the current model and write it out as a LP format. Finally, we optimize it. Okay, so once I execute it, and it takes about 30 milliseconds. Okay, and here actually solution time is much less. So here what we have, and actually the heuristic solutions already find this optimal solution. It finds 2 and 4 are actually in our case is 1 and 3, because we're using a start from 0. So this is using Gurobi to solve it. And Gurobi was very intelligent and directly using his heuristic solution already find the optimal solution. So there's no syntax iteration needed. Of course, other formulation, other problem could be a little bit more involved. Okay, an objective function equals to 2. I only need two fire station install, and which city they are. So here we're going to do the analysis. First, we're going to print the fire station plan. So for all the CT in the bill key, if the bill CT.x, which is its value, is greater than 0, then I print out set up a fire station in city. Okay, so here is CT1 and CT3. Actually, if I can revert it to original, we could just using +1. So here I don't worry about it since we the CT start with 0. So you know there's a second CT and the fourth CT. All right. Next, we're going to do some demand fulfillment matrices, matrix. And here we say total population. And the first part, we calculate the total population. Is just using a for loop to accumulate all the population among 6 cities. And now I'm trying to do is cover population for each one of the fire station. So we want to see how each one of the fire station cover what percentage of our total population. What I do is similar to that previous for loop, but if the value of solution equals greater than 0, means I'm going to build a fire station in that city, and then also I'm going to calculate total sum of the population, K, and K is one of the city, but if K is also in the coverage. So look at this sum function we're using right here. It's very interesting. The K is in the coverage CT. CT is one of the city for that currently built. And then we're going to sum all the K together. So for all the covered population, and that's I want to do a subtotal. So cover the population for the CT1 and CT3, and we're going to print it out. So after we're done the subtotal, and again, I'm going to do CT in range for the length of a covered population, which is 6. Again, if the covered population is greater than 0, and then I printed out the covered percentage. So the covered population for the CT divided by total population, overall population times 100. So they give you a percentage. So fire station number cover how many percent of the population. And this is a print, and total, I'm going to print the vector of a covered population. So here I'm going to run it. And you see that fire station 1 covers about 44.75, 3/4, or 44.75 of population. The other one is the fire station and covers 55.25 of population, and the vector down there is the covered population percentage. So this is a fairly show you how to get answer out of the Gurobi models and solver and print it in a nicer format to produce report. Okay, well, I hope this is going to be helpful for you. Last one, we're going to see the resources utilization matrix. So we know that from the very beginning and the data, we have budget, we have 20, and each one of fire station we build, these are the costs for that. So here we have CT1, I have a 6.1, CT3, I have 5.5 in that case. See how much percent of the budget we're using. So similar situation, we total cost initialize equal to 0, then using a for loop to see from range from the number of city we have. If the current solution is greater than 0, I accumulate the cost for that. Okay, so so budget consumption is basically total cost divided by total budget and times 100 and round it down to two digit. So the percentage of a budget consumed associated the fire station building plan, as we using up about 58% of our budget. The last two is more of formulating your report and doing some analysis based on the solution you get from Gurobi. And this pretty much, this is an interesting problem. Actually, for the population and the cost, we didn't use that in the Gurobi model. And we can actually build in the population coverage is as part of our objective function, which can be maximized coverage possible. And also, the coverage should be could be percentage of cover. Okay, how much percentage of the population we can cover, and the cost we can also want to have minimize associate costs. Okay, so that means this C cost times each one of each one of the variable could be a minimization problem as well. So you probably see that from this so-called basic rudimentary example, and you can see a lot of extension and enhancement, and for you to using this basic model to solve a variety of application in that sense. Okay, I'm going to conclude this lectures